Hello everybody. Today we are going to see this last section which starts from design of database. Let's begin. Database design is similar to the pillars of a building. Any negligence, errors in database design may lead to degraded performance of the software. In some cases, such as real time applications, it may also lead to disasters. The following are various steps in database design. Selection of database architecture, designing database schema, selecting indexes, estimating capacity of the database. Selection of database architecture. Selecting database architecture is one of the most challenging parts of database design for any information system. Before deciding on the target DBMS where the database is to be implemented, few considerations are required. Hierarchical database structure is a kind of database management system that links records in tree data structure such that each record has only one owner. For example, an order is owned by only one customer. It resembles a tree structure. Network database structure is more flexible structure than hierarchical model as well as relational model but not preferred due to the high processing time. A neural network is an example of network database. Relational database structure is most commonly used database model. The data is modeled as a mathematical relation. A reference key joins different tables together. Indexes provide rapid access to a specific record in the database. For example, DB2, MySQL, Oracle are some RDBMS. Object-oriented database management system is based on object-oriented paradigm. In object-oriented database, data is stored as objects and can be interpreted only by using the method specified by its class. A blueprint of the database is a physical model. A schema defines the database in terms of tables, keys, indexes, and integrity rules. A relational schema consists of a relation, name of the attributes in the relations, and restrictions on the relations called integrity constraints. A database schema is a set of relation schemas. Changes to a schema or database schema are expensive. So, careful thought must be given to design of a database schema. The following are some guidelines for the design of a database schema. Each entity should be implemented as a database table. Each attribute should be implemented as a field. Each table must have a primary key and an index based on the key. Each table may have zero or more secondary keys, appropriate foreign keys. The following is an example of a database schema. Employee EMP underscore name, birth underscore date, social underscore security underscore number, department underscore name, department under which come department underscore name and function. So these are an example of a database schema. Figure 9.10 depicts the database schema of the above. One too many, like here employee name, birth date, social security number, department name, and in department comes department name function. So 9.10 is a database schema. A database schema defines a database in terms of tables, keys, indexes, and constraints. The following are various objects of a schema: fields, records, tables, database. Selecting indexes during the process of file and database design. One must choose index based on a single field, usually the primary key or multiple fields. While selecting index, one must keep in mind the performance issues vis-a-vis the issue of inserting and deleting records. While indexes can be used generously on tables primarily used for query purpose with rare necessity to update records, they should be used judicially, judicially in tables that support transaction processing, which involve large insertion, updation, and deletion operations. The amount of time needed to maintain the indexes in database tables increases with the number of rows stored. When an index is created on a table, a separate storage area is located to store the index structure. Database table can have one or more indexes associated with it. So figure 9.11 index created on the employee ID field is an image, so it is not available here. For example, consider an employee record. Figure 9.11 depicts an index created on the employee ID field of the employer table. The index table contains a sorted list of the employee ID values. Indexes may significantly improve the performance of SQL queries. It may not be noticed with small tables, but it can be quite significant for larger tables. However, there are disadvantages of too many advantages to having too many indexes on table. Indexes can slow down the speed of some inserts, updates, and deletes when the DBMS has to maintain the indexes as well as the database tables. Also, indexes take additional disk space as they are stored separately. Example: in an employee database table, one will retrieve records based on employee name, department, or hire date. One may create three indexes: one on the department field, one on the last name field, and one on the hire date field. The indexes are created on fields that appear in where clause or select statements. If the Boolean operator in the where conditions is and, for example, city is equal to Mumbai and state is equal to MS, then a concatenated index on the city and state fields will help. This index is also useful for retrieving records based on the city field. If the Boolean operator in the where condition is or, for example, department is equal to EDP or higher date is greater than 133, so an index does not help performance. Therefore, index file need to be created. Estimating capacity of the database. Database administrator needs to calculate the amount of disk space required for the database. In a given table, calculate the record size by adding the sizes of various fields in it. Also, the number of records that will be present in each table at a particular period of time should be forecast. Table size is equal to record size into number of records in the table. Database size is sum of sizes of all tables in that database. As rule of thumb, add a factor of 50% for indexes and other overheads to get the expected database size. While designing a database, future growth of database should also be kept in mind. Most of the business database have a linear growth trend. Figure 9.12 depicts the growth of a database in relation to time. Database size, growth of database. So here we come to the end and check your progress is here. What is case study? The physical database design is a process of transforming a logical data model into an actual working physical database. A logical data model is required before designing a physical database. We will assume that the logical data model is complete, though we will consider physical database design targeting a relational DBMS. The very first step is to create an initial physical data model by transforming the logical data model into a physical implementation based on the target DBMS to be used for deployment. In reality, the physical data model depends largely on the target DBMS to be used for implementing the database. Therefore, to successfully create a physical database, design requires a good working knowledge of the features of the DBMS, including Knowledge of the database object supported by DBMS, the physical structures and files required to support those objects. Details regarding how the target DBMS supports indexing, referential integrity constraints, data types, and other features that augment the functionality of database objects. Knowledge of the DBMS configuration parameters and limitations, and data definition language DDL to translate the physical design into actual database objects. We can create an effective and efficient database from a logical data model, that is ER diagram. The first step in transforming a logical data model into a physical model is to perform a simple translation from logical terms to physical objects. It may be noted that this simple transformation will not result in a complete and correct physical database design. It is simply the first step and can act as a template to further refining the database design. The transformation consists of the following steps: transforming entities in ER diagram into database tables, transforming attributes into table columns, and transforming domains into data types and constraints to primary key and foreign key relationship. Designing a primary key is an integral part of the physical design of entities and attributes. A primary key should be assigned for every entity in the logical data model. One should try to use the primary key as selected in the logical data model. However, if suitable attribute is not available, multiple attributes can be used as primary key. It may be required to choose a primary key other than the attributes in logical design by inserting a column that does not store business data. Surrogate key for physical implementation. In a physical database, each table column must be assigned a data type supported by the DBMS. Certain data types require a maximum length to be specified. Example, a character data type could be specified as char25, indicating that up to 25 characters can be stored in the column. Figure 9.13 depicts the ER diagram of an employee database. After following normal steps of transformation described above, further refinement of relations is possible before implanting on the target DBMS. One such example is shown below. In the above ER diagram, department being a multi-valued attribute, we will convert this multi-valued attribute into relation, namely department. So here we can see a physical file design and database design. Okay. Figure 9.14 shows the nearest relation database schema for the ER diagram depicted in figure 9.13. The aim of database design should be to create a database plan to fit present and future objects. A logical data model should be used as a blueprint or for designing and creating a physical database, but the physical database cannot be created properly with a simple logical to physical mapping. Physical database design decisions need to be made by the database administrator before implementing physical database structure to the target DBMS. Sometimes this may require deviation from the logical data model. Summary. Traditionally, file is being used for keeping data. Use of DBMS has been the standard to store data for today's information systems due to their various advantages. Any physical database design involves steps like choice of target DBMS on which the database is going to be implemented. Relational database is mostly being used unless the application has specific requirements. The physical database design process can be considered as a mapping from logical model to physical working database, which involve design of fields, design of records, and finally design of the database. While transforming the logical model to physical model, many implementation issues related to the information system and target DBMS are to be addressed. Database volume estimation is an important part of database design. The present size and future growth of database is to be estimated before implementing the database. So here we come to the end, and till then keep exploring.